Today we're going to go beyond, more on PageRank. You're going to become super expert on PageRank. First, I want to pause a moment to pay our respect to those in Ukraine who are fighting for their freedom and for our freedom too. Today we're going to go much deeper into PageRank. Last time you saw the introduction, the first cut. Now we're going to go actually and investigate many things. These slides are actually from a colleague of mine called Sarunas Gurdzijauskas, who is a professor at KTH. Okay, so I'm going to present that. We're going to talk about random walks. I mentioned already random walks. We're going to go much more into random walks. We're going to talk about eigenvalues, matrix representations of that, PageRank as a random walk, but you have to fix the random walk. You have to make the web graph strongly connected and aperiodic for the random walk to work. This corresponds to the evaporation. Then beyond PageRank, topic specific. PageRank tells you the importance of a page, but we want to know the importance with respect to a specific query. So that's topic specific. Also, we want to do something similar to PageRank. We want to find pages that are similar to a given page for kind of similarity. That's another use. This is an algorithm called SimRank. And finally, I'm going to tell you how link farming works. This is also called web spamming, how you can cheat on the PageRank, and how you can try to avoid cheating using a scheme called TrustRank. Okay? First, I want to talk about random walks, and I want to give a lot of intuition now. Okay, so please listen carefully. I'm going to try to introduce all the ideas with intuitions. Here is a graph. Underrated graph, okay, connected. Start with some node, V, could be any one of these nodes, and we move to another node, like from this node, we move to another node with a given probability, but the probability is 1 divided by the degree of the node. So the degree is the number of edges, so 1/3 here. So you walk around like that, and each time you choose an edge with probability, this sequence of nodes is called a Markov chain, something you may have seen. And if you have a state machine and you go from one state to the other according to probabilities, and you have no memory, okay? Each time you go in a place, you're there, and then you don't worry about where you come from. You just keep going. This is a memoryless sequence. It's called a Markov chain. So these random walks are Markov chains. Okay? So let's say now, so we have our 5 nodes, and let's say we have a probability of being in each node. Okay? Node 1, let's say times 0, we're at node number 1. Okay? Probability 1, all the others are node 0. And now we're going to do steps. One step after the other. So the first step, 1 is going to go to 2 and 3. So you have 50% chance to go to 2 and 3. The others are still 0. Then if you keep going, you will get more. So from 2 and 3, notice you are combining the 2. So you have 42% going back to node 1, because both 2 and 3 can go back. 42% going to node 4, because both 2 and 3 can go there. 17% is going to node 5. And you can keep doing that and calculating probabilities. Okay? And so this turns into something like this. And so these probabilities are changing all the time. You notice they're jumping around here. So what happens to this sequence? If you keep doing these walking around, will you have some kind of convergence? We have fixed probability. Okay? So we have some fixed initial node. but you could also have some other kind of beginning, yeah? Okay, so does this converge? Well, looks like it. After 30 steps, we have 17%, 25, 25, 17. So it looks like nodes 1, 2, 3, and 4 have more chance than the others. Okay. And you can prove, which I will not, but I will give a lot of intuition, for any connected, non-bipartite, bidirectional or undirected graph, and any starting point, the random walk converges. And we'll see it has to be connected and non-bipartite. If you don't have that, it won't actually converge. Okay? And there's some unique stationary distribution. So stationary means that if you keep doing more steps, the probabilities stay the same. They're stationary. Okay? And this is called a power iteration because we'll see we're going to have to do powers if we start doing the matrix representation. Okay, now notice you have this very interesting convergence, 17, 17, 25, 25, 17. How do you calculate those numbers? How do those numbers, how can you calculate them? You can actually show that it's very uniform. So pi here is the converged walks. So the probability of ending up in a vertex V, pi of V, is the degree of V divided by 2m. So the degree is the number of edges coming out or in, and m is the total number of edges. So 2m, each edge actually counts twice. This edge is counted twice, so you count it twice. So it's very simple. I have 1, 2, 3, 4, 5, 6, that makes 12. Here I have 3 over 12, 2 over 12, 2 over 12, 3 over 12, 2 over 12. So the calculation is very simple. Okay. If the graph is D-regular, so a D-regular graph is a graph where every edge has D, every node, has D edges. So this graph is not D-regular. So if they all have the same number of edges, then the distribution is uniform. It's the same probability. So it all evens out. Okay? So that's interesting, for the random walk. And you can actually show that this is actually a fixed point. Okay? So say we have a node. We have it going from U to V. Okay? So the new probability of being in edge V is the probability of being in edge U multiplied by the chance of taking the edge going to V. Now this is a sum over the edges going from U to V. So this is the probabilities where you're all going to V. If this one here is du over 2m, then you can compute it, and it turns out to be dv over 2m, so it's the same. So it's an actual fixed point, stationary distribution. Okay? So that's, you can show that. So that's interesting to know about random walks. Okay? So now we know something about random walks. This stationary distribution, so the one we get in convergence, the probability is proportional to the degree of the number of edges coming out of the node. So there's an intuition on that, okay? And the intuition is, the more neighbors you have, the more chances that people will visit you. And that's a good intuition, okay? So if I have 5 neighbors, I will have more visitors than if I have 2 neighbors, okay? Okay, so that gives you some intuition about the random walks. And we're going to use that now. The next step is we're going to go to a representation. We're going to code all of what we did now, we're going to coded in terms of matrices, okay? So here's our little graph. We're going to first represent it by what's called an adjacency matrix. So if there's 5 nodes, this is 5 by 5, and each value is either going to be 0 or 1. So 1, Aij is 1 if there's an edge going from I to j. So it's very intuitive, huh? The adjacency matrix. Okay? So you understand the adjacency matrix? This is the basic thing that we're going to use, huh? The adjacency matrix. Now we're going to do some computations. So here's another matrix, D. This one is a diagonal matrix, and the element on each diagonal is 1 over the degree. Okay? So for our graph, it'll be 1/2, 1/2, 1/3, 1/3, 1/2. So 1/2, 1/2, 1/3, 1/3, 1/2. And now we're going to start doing matrix operations. If you multiply D by A, basically what happens is that each of the 1s is going to be turning into a fraction here. And actually it's probability. So this matrix M is called the transition matrix. And this gives us the probabilities. So if I'm in node 1, I have 1/2 the probability of going to 2, 1/2 of going to 2, and 0 for going to 4 and 5. If I'm in node 4, here, I have 1/3, 1/3, and 1/3 for going 2, 3, and 5. So this is like adjacency, except now it's giving probabilities. Okay? That's all very simple, right? Good. The adjacency matrix is actually a very interesting, useful matrix. So Aij is 1 if there's an edge, a link between I and j, in other words it's 0. So it's very easy to understand. And it actually, you can see it gives us all 1-hop paths. Every time there's a 1, that means there's a path with 1 edge, which I call 1-hop paths. But now we can do more interesting things. Let's say we want to count 2-hop paths. We want to say how many paths are there from this node doing 2 steps to another node. From I to j, 2-hop paths. Maybe there's many, or maybe there's none. How do we count them? With the adjacency matrix, it's actually very easy. We just have to do A squared, A times A. So why does that work? Well, if you look at how matrix multiplication works, you can see that you're actually, if I make a little diagram here. So A times A. So if I want to compute some node here, I will do something like this. I will compute it like this, and here I have 1s and 0s. Okay? Now, if there is a path, so here I have ij, here I have I, and here I have k, okay, the k's, and here I have k's, and j. I go from I to k, and then I go from k to j. That's a 2-hop path, From I to k, and from k to j. And if both of these are 1, then this is going to give a 1 here. And if I count all of these, this will give me the number of 2-hop paths. So that's neat, huh? The adjacency matrix gives you this useful information. Okay. So A squared gives us 2-hop paths. A cubed, what does A cubed give us? Well, it's A squared times A, So basically we have a 2-hop path plus one more. Okay? It gives us the number of 3-hop paths. So you can see the powers of the adjacency matrix. It tells you how many paths there are. Okay? Okay, let me make a little bit of a technical adjustment. So graphs, there's lots of definitions. Technically, it's not a path but a walk. Okay, that's a weird distinction. Okay, a path goes from nodes to nodes, but a walk follows edges. In French, it would be un chemin et une marche. Okay, so this is a graph theoreticians. But for this particular case, it's the same. We don't really care if we're going from nodes to nodes or we're following edges. Because here we're following edges, okay? But in fact, we're counting walks. But in this case, it would be the same as paths. That's just to be very precise in terms of graph terminology, okay? So what if you take a vector now? 1, 0, 0, 0, 0, and you multiply by a. What does that mean? Okay. What does it mean now? Well, it means if I start here at 1, then I will be going to either these two here. Okay. So it's basically the number of paths that start at 1-hop paths. Okay. Or walks, number of walks of length 1, starting from node 1 and ending up in node I. I goes from 1 to 5, Okay, so you see we're going to start doing interesting things here. What about v times a squared? Well, it's the number of walks of length 2 that start from node 1, okay? And so on, And the cube 1, VA cube, which is 0.4512, is how many walks of length 3 from node 1 end up in these nodes. So you can see you can do all kinds of interesting graph computations by doing matrix computations. Okay? Okay, good. So that's the adjacency matrix. Let's look now at the random walk matrix. So the random walk matrix is the one where you have fractions, also called the transition matrix, giving you the probabilities. It doesn't actually count how many, but it gives you probabilities. So if you take the same vector, 1, 0, 0, 0, 0, multiplied by this transition matrix, you actually get the probabilities that you end up here. A half, and these have 0 probability. See that? It's not very complicated. But if you keep going, if you take this one, 0, a half, 0, 0, and you multiply again, then you get the probabilities. So starting with these probabilities, you end up with these probabilities. Okay? So you can see each time you multiply, you're going farther. Okay. Okay. Very good. So we start from a node, V0, and after t steps, we are at node Vt, and we move to a neighbor with probability 1 over dVt. So the sequence of nodes, Vt, is a Markov chain. Okay. Let's now start with the initial state, P0. So probability 1, we're in node 1, 0, we're in the others. Okay. Okay. Or it could be something else. And now we can say, after t steps, Pt is P0 times m to the power t. Okay, right? It's simple. Or if you like column vectors, you can say Pt is the transpose of m to the power t times p0. I'm not really going to make be so picky about column or row vectors. So here the p's are row vectors, so you multiply on the left side. Okay? Okay, good. So we keep going now. So here it starts with 1, 0, 0, 0, 0. We get after one step. We go after 2 steps. Okay? And we keep going. And if pt plus 1 is equal to pt, then we have converged, right? We have reached our stationary distribution. And let me call this one a little pi. A p is a capital, little pi is like a small p. This little pi is the converged distribution. So this is not 3.14159, huh? It's a converged distribution. So pi times m is equal to pi. So this is like fixed point in the matrix. Okay, you take pi, multiply by m, you get the same vector. Okay? Now we can connect to eigenvectors and eigenvalues. Vector pop, value pop. So these are called eigenvectors. So if you take a vector v and you multiply by matrix m, and you get some number, some real number times v, then v is an eigenvector. So it's kind of a special vector for that matrix. And lambda is a special value called the eigenvalue. Okay? So pi is eigenvector of m with eigenvalue equal 1. That's the convergence of the random walk. Okay? That's pretty straightforward, right? So, okay. So let's go on now. Let's start studying now these eigenvalues. Okay? Remember, so this is what we reached. Pi times m is equal to pi. And we have the eigenvector v and eigenvalue lambda equal 1. Okay. There is something called the spectrum of a matrix, which is basically the set of all eigenvalues, because usually there's a bunch of them. So here, let me just show you an example. Let's take a D-regular graph. D-regular, remember what it means? Each node has D edges. What is the meaning of A times X? Okay. So X is a vector that has values for each node. Okay. And now this is the equation of how you multiply a matrix by a vector. Okay. This is the formula. And an eigenvector is this. Okay. To write it out completely, we have this. A times the vector x as a column vector is lambda times the column vector. Okay. Okay. Now let's take our graph. All nodes have degree D and G, so this is the graph G, and it's connected. Okay. It only has one component. Okay. What are some eigenvalues? So what I want to do is give you some intuition on this, because these eigenvalues and the vectors, they mean something on the graph. Okay. So we have a graph which is all the nodes is degree D and it's connected. That means there's only one big component, and A is the adjacency matrix for this. Okay? So let's say we take the vector 1, 1, 1, 1, 1, all ones, and we multiply by A, okay? Or A times X if it's a column vector. Well, since each node has D things coming out of it, if you look at the row, there's going to be D places where it's equal to 1. And if you add them all up together here, you get D. And for all of them, you will get D, 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 D. You will get all D's for this special graph. Huh? Remember, this is special graph. Huh? D regular. So for D regular graph, D is actually an eigenvalue. Okay, this degree, the degree actually means something on the graph. You see it, huh? We found, and it's called an eigenpair. If you take the vector, all ones, and the eigenvalue together, this is an eigenpair, the eigenvector and the eigenvalue. This is the principal eigenvector. Okay, so there's a bunch of them. You can organize them in terms of the biggest ones and so on. But this is going to be the main one, the principal one. Okay? So that gives you a little bit of intuition, huh? For this special kind of graph, the eigenvalue is actually kind of the degree of the nodes. But it's not always at that. Let's look at other graphs now. So this is kind of simple case, huh? What if the graph is not D-regular? What if we have different kind of graph? Okay, things start getting interesting, and I want to give you some intuition on that. Okay? Okay, so let me first recall what's called the spectrum, or the spectra of a graph or of a matrix. So if we have V times A is lambda V, and lambda is an eigenvalue, if A is a real symmetric matrix, okay, which means basically we have undirected graph now, then all the eigenvalues are going to be, we can organize them, they're real numbers, and you can have the biggest one, which is lambda 1, all the way up to lambda n, and the eigenvectors are orthogonal. Okay, the orthogonal vectors in space. That's something we can know. If G is a D-regular graph, this very special graph, then the principal one, the biggest one, is D. So this eigenvalue is actually related to the degree. Okay? For this graph, for the adjacency matrix, for a random walk matrix, actually, because of the convergence, because of the probabilities, the main eigenvalue is going to be 1. Remember, pi times n is 1 times pi. It's not d, but it's 1. Okay. Okay, this is a small detour. There's another kind of matrix called a graph Lupulation matrix. You take the adjacency matrix A, and you do D minus A, where D is a matrix where every entry, every diagonal gives the degree. This gives you a funny matrix, and the sum of all the rows and columns is 0. Okay? And this is a funny matrix because you can say G has k connected components if lambda k is equal to 0. Okay, so this Lupulation is sometimes important, so I mention it, but we're not going to use it in the rest of the course. I mention it here because if you start looking at things on graph theory, you see this one, and you can see this funny connection with graphs. If lambda k is 0, then G has k connected components. So there's a connection between the eigenvalues and the connected components. Okay, so this was a detour. So now you can forget about the Lupulation for the rest of the lecture. Okay, so all of the eigenvalues together is called the spectrum of the graph. It kind of gives you all the special values. Okay, and for different kinds of matrices, adjacency matrix or transition matrix or Lupulation, which we're not going to use, you get the spectrum. Okay, and it's interesting. You can actually study them. And if you look at the difference between the first two, the biggest ones, lambda 1 minus lambda 2 actually means something. It's called the Eigen Gap, or spectral gap. So this difference between those two eigenvalues actually means something, and I want to give you some intuition on that. Okay? In the case of a transition matrix, we know that lambda 1 is equal to 1. Huh? But lambda 2 might be some smaller value, so it's the difference between 1 minus lambda 2. So what is this Eigen Gap thing? What does it mean? Well, it actually means something when the graph is connected or disconnected. So let me show you what I mean. So assume the graph is disconnected. Okay? If a graph is disconnected, maybe it has two components. So if you start your random walk in the first component, it'll stay there, right? If you start your random walk in the second component, it stays in the second one. So you can see that there's some connection between that and the random walk, huh? This disconnected nature, okay? It turns out, if the graph is disconnected, lambda 1 is equal to lambda 2. So if the graph is disconnected, the Eigen Gap is 0. That might seem very weird, okay? But I want to show you why it's like that. And you'll see it's actually intuitive, okay? To give you some intuition on that. So here's an example. Let's say I have a graph, G, with two components, A and B, okay? Each of the components, so this is a simple case, each one of them is D regular, so all the nodes have degree D. Now, let's take a look at this graph and look at the eigenvectors, and we can see some interesting things. So let's say we put all the ones on A in the vector and zeros on B. So it's like we're starting in A, okay? If you multiply A times, so if I have this, so all the ones are on A, the zeros are on B, but there's never a connection between A and B, okay? If you do A times X prime, you will stay in A. That's intuitive, huh? If you do random walk from a node in A, you stay in A, and you never go to B. But if you do random walk starting on B, here, the B's are all ones, A times X double prime, then you will have only the D's are only on the B case. So if you start on the B, you do random walk, then you stay in B, okay? Notice you have two eigenvectors and two eigenvalues here. X prime is an eigenvector, X double prime is an eigenvector, but different one. Here we have D times X prime, here we have D times X double prime. So we have two different eigenvectors with the same eigenvalue. We have this. Okay, lambda 1 is equal to D, lambda 2 is equal to D, and we have two components. So the Eigen Gap is 0. Okay, that's interesting, isn't it? I mean, there's this connection. You can see there's a connection between the Eigen Gap and the splitting of the graph to components. Now let's say we do a little bit something different. We add a small number, a few connections between A and B. Just a small number of them. It turns out that the difference between lambda 1 and lambda 2 is going to be small. It's going to be close to 0. Okay? So the Eigen Gap, actually, if it's 0, you mean then the graph is disconnected, at least two components. But if it's small number and it's not 0, then the graph is like almost two components. So it's this Eigen Gap thing tells you how you could split the graph. Okay? So that's interesting, right? I mean, that gives some intuition on connecting graphs and eigenvalues. Okay? Let me now give you some kind of conclude on this a little bit. Let me now talk about the convergence of the random walk and intuitively show you why it's like that. So the idea is for every connected, non-bipartite, undirected graph G, the distribution converges to a limit and unique stationary distribution pi. Okay? And it has to be connected and non-bipartite. And if G is regular, that means all the nodes have same degree, then it's a uniform distribution. So that somehow the distribution, how uniform it is, shows you how uniform the degrees are. Huh? But now we can make some intuition here. Huh? Okay. Okay, why connected? Okay, well, if it was not connected, there would be no unique stationary distribution. If it's not connected, if you have components A and B, you could have one distribution where it's all A and another one where it's all B, so there's no unique stationary. So it has to be connected. Remember the Eigen Gap discussion. Why non-bipartite? Bipartite, remember what it means? We already saw that in the course. You have two sets of nodes, and you go from one to the other. Well, if you calculate probabilities, you will have, in the bipartite case, you will be on one side, you do one step, and then you're on the other side. You do one step, go back to the first side, so you're hopping back and forth. So the probabilities go from two different values. They're oscillating. Okay? So if it's bipartite, you don't have this limit. You don't have limit, okay? Because you have this oscillation between the two sides. Okay? Okay, you see that? So that's why it has to be connected, non-bipartite, because you want unique, and it has to be limit. There has to be some limit that's not oscillating, and it has to be one thing and not two possibilities. Okay. Okay, so that gives you this intuition for undirected graphs. What about directed graphs? Okay, let me give you some intuition on that. So here's a directed graph. Okay. Okay, the directed graph has to be strongly connected. We saw that already last time, huh? That means there has to be a path from every node to the other. Otherwise, we can say the walks that will leak. In fact, you end up in these leaky places that you will not come out of. Okay? Like here, for example, here you have a strongly connected one. Huh? So the second case, it has to be aperiodic. So this is kind of generalizing the non-bipartite. So the graph has to be somehow mixed. If it's periodic, that means it's basically doing the same thing in the same number of steps. So in this one, for example, I go 1, 2, 3, and I'm back here. 1, 2, 3, and I'm back. So the graph is kind of following the same cycles in both sides. And if you have that, again, you have a kind of oscillation, okay? So it has to be strongly connected and aperiodic. So I'm not going to prove that. I give you just the intuition on that, okay? So basically, the greatest common divisor of the lengths of all cycles is 1. But here I have 2 cycles, 3 and 3. The greatest common divisor is 3, so it doesn't work. Okay? Okay, so that gives you intuition now about graphs and random walks. And now I'm going to change. So the first part of the course was kind of theory part on random walks and matrices and giving you some intuition. But now the second part, we're going to start talking about PageRanky things. Okay? So let me now give you a view of the history of web search and how Google came to be the king. Okay? So this is, now I'm going to go through history. Long time ago. A long time ago, probably many of you were not even born in such an old period, in the 1990s, but it was very weird. The internet already existed, we had telephones and electricity and running water. Sometimes people don't believe that we were not living in caves in 1990, but it was still, this was the first web search. The web was invented. The first generation was manual curation. Yahoo came in those days, and they had little gnomes or people sitting in a dark room coming up, trying to come up with these classifications. Okay, so in those days, it was manual. That was the very first generation, but that doesn't scale. Okay, the web was already growing exponentially. Okay, and then there was the second generation. Now the second generation was like classical information retrieval, where you look at the text in the pages, and all the pages that talk about Star Wars, you put them in film Star Wars, okay? And it's just classical indexing stuff, okay? And a famous browser in the search engine from those days is called Alta Vista, which probably you have never used. I actually used it, okay, a long time ago, very long time ago. Here you can actually spam it, you can cheat, you can do something called term spam, which I will explain how it works. Okay, you can spam this. But the second generation was still not very good. And then Google invented PageRank, which was completely automatic, but it actually was able to figure out the importance. And it's based on inlinks, so it's not based on the text in the pages. See, it's very easy to cheat for text on pages. You just put anything you want. You could say, this is the world's best page or something, okay, in there. But you cannot fake inlinks, or it's not so easy, because it's other people pointing to you. Okay, so PageRank is based on inlinks, so it was much harder to fake that. Okay, so here is then another explanation of the PageRank idea. Remember last time I talked about a fluid, liquid, and there was also the random walk. But let's talk about votes now. Each page has some votes, a collection of votes, and he distributes them to all of the outgoing links. And 100 votes and 5 outgoing links, each link gets 20 votes. Okay? And then the votes go to the next one. Okay? RJ budget votes, n outlinks. Each link gets RJ over n votes. Okay? And then the notion is a vote from an important page is worth more than another kind of vote. Okay? And the importance of a page is the sum of the votes on the inlinks. So a lot of important people pointing to you makes you important, and the more people there are, the more important you are. Okay? So what does this look like? Well, this sort of looks like random walk. You go out, and then you come in, and you go out, so you keep going, you're circulating around. It's kind of like random walk. Okay? Okay, so Google PageRank then is the principal eigenvector on the transition matrix of the web graph. Okay? That is the basic definition of PageRank. Okay? And now the trick is, for Google, the trick is, how do you compute that thing? Okay? Okay, you have to do iterations, power iteration. And remember, this is kind of the structure of it. So if you do that, what's going to happen? So as we saw before, there's going to be some problems here. So remember, this is kind of the, I briefly went over this before, this structure of the web. You have these disconnected components here. So of course you're going to have problems. Does this graph have a unique stationary distribution of the random walk? Well, no, it doesn't. Because it's not strongly connected and aperiodic. It might be aperiodic, but it's not strongly connected. Okay. What is the problem? Well, it's a directional graph. Okay. Look at this one. So we can actually give names to some of these problems. This problem, where all the nodes, all the arrows go to one node, this is called a dead end, a cul-de-sac. It's a node with no out degree. So once you get in there, the votes, they're lost because they don't come back. The votes, they leak. So I remember these, because you never see them again. So this one was called a dead end. There's another kind of a problem. This one has a funny name called a spider trap. So it's not one node, but it's a collection of nodes. And this collection only has arrows coming in. So all the nodes, they stay here. You can see it's like the little spiders that are running around here, but they never go out. Okay? So this one is called the spider trap. Okay? Dead ends and spider traps. Well, the World Wide Web is not strongly connected. Okay? Remember, the condition was strongly connected and aperiodic. Okay? So this doesn't work, which we already saw before, but here you can see another view. It doesn't work. You have to make it strongly connected. So we have to fix it. Okay? So how to fix it? Okay? Well, remember we saw there's two conditions. It has to be strongly connected and aperiodic. Probably there's no problems making it aperiodic. It's not like the whole web is kind of a thing with everything cycling at the same frequency. But you do have to make it strongly connected. Okay? So the Google solution is you make small links, tiny, tiny links, from every node to every other node. Okay? This is what we called the evaporation and the rain falling. And with that, you make sure that the whole graph is connected. Okay? So if you have the original graph here, you have a complete graph here where every node is linked to every other node with a small probability that you take that link, but it's linked everywhere, and then you combine them. Okay? Do something like this. And once you do that, when you do that, you can actually fix, then the PageRank works. But in terms of matrices, it's different now. Okay? So what happens is, the Google random walk will follow the real link with some probability. So now we're calling it beta. In the previous lecture, I called it S. It follows it with probability beta. With probability 1 minus beta, it just jumps to random page. Okay? Which is modeling the water flowing down and the evaporation. Okay? And the beta is going to be 0.8 to 0.9. This means that most of the time you follow the link. The random walker will teleport from any spider trap after 5 or 10 steps. That's how you could say that. If you get stuck in a spider trap, then eventually, ping, you jump out. Okay? So this is a nice way to summarize it. Random walker will teleport from any spider trap after 5 or 10 steps. Okay? And for dead ends, once you're in the dead end, you always teleport because there's no link to follow. So in fact, in that case, the probability will be always going to the other node. Huh? Okay? So here's a graph. So here's our transition matrix. This is the transition matrix of the original one, but we're going to compute a new transition matrix where we have the beta, the jumps. Okay? So here's our second graph with our jumps. And it has, which this one I'm going to call the teleportation matrix. So if I'm in node 1, I jump to each of the other nodes with 1/4 probability. That's the teleportation. And now I'm going to add them up. Okay? So, boom, bring them together. And this one is multiplied by beta. This one is multiplied by 1 minus beta. So that gives us this. Okay? The PageRank matrix. It's not just this one. It's this one times beta plus this one times 1 minus beta, except we have to be careful when there's a dead end. When there's a dead end, it's actually 1 here, because there's no way out here. Here we have dead end. So in case of dead end, you have to put 1 here and not 1 minus beta to make the probabilities be okay. So that is the PageRank matrix. Okay, beta and 1 minus beta. Okay, this is what I just explained, that right? You have to be careful about the dead ends. Okay, so that gives you a complete PageRank matrix. Okay, and is that good enough? Is it fixed now? Well, let me make a small break, and then we'll see how to compute this. So last time we talked about random walks. But now we're actually doing huge matrix computation, okay? So let's see how to compute this. But first, we make a small break now. The actual matrix with the teleportation. So basically, all we have to do is calculate the principal eigenvector. It's this matrix, and it's done, right? Right? So this fixes it, kind of, right? Well, almost. So first of all, beta cannot be 0. It's different from 0, okay? But still there's some problem. It's actually a practical problem now. So we have this big matrix, and we want to calculate, you basically calculate the eigenvector. You can do some kind of a convergence calculation. But actually there's a lot of web pages. Let's say we have 10 billion pages. 10 billion, okay? So what does the PageRank matrix look like if you have 10 billion pages and not 5? No. You have a lot of elements, okay? The random walk matrix is dense. That means most of the entries are non-zero. You have n squared non-zero elements. N is equal to 10 billion. That makes 10 to the 20th elements that are non-zero. That's a lot, and I don't think there's any computer that can compute that. And even nowadays, the web's even bigger. Can you even store it in memory? No, you cannot even store it in memory. So you can't just take this matrix and compute with it. It's too big. Okay? So you need some kind of a technique to make it smaller. Okay? So the fix, there's actually a way you can make it smaller because it has some kind of structure. It has this teleportation. So teleportation is like a number that you add everywhere. The same number. You add it everywhere. And if you do that, you get this very dense, huge matrix. Okay? But if you're a little bit smarter, you could do it differently. Since the teleportation is always the same number you're adding. It's 1 over n. You're always adding the same number. It's kind of like a tax, a fixed tax that you pay everywhere. Okay? So basically, instead of doing like this, where you take the old vector and you multiply by PageRank, which is this 10 billion by 10 billion matrix, you get the new vectors. This is kind of too hard. You actually use M, which is the matrix without teleportation, okay? It's just adjacency matrix, which is much smaller, okay? And if you look at it, actually, the computation, you're adding like a constant here to this, okay? A constant vector. 1 minus beta over n. N is like 10 billion here. The n is 10 billion. And here you have like a vector. This vector has 10 billion, which is already a lot. And this matrix is 10 billion by 10 billion, but most of the entries are zeros. Okay? Because most web pages only have a small number of links. Very small. I mean, 10, 20, maybe 100. So this is just a 10 billion times some small number. If you look at the number of non-zero entries, okay? So if you do it like that, then it's much easier. So M PageRank is dense. It has 10 billion times 10 billion non-zeros. But M is only a small multiple of 10 billion. This is called a sparse matrix. Une matrice creuse in French. This is a dense matrix. Usually when the matrices get very big, you try to use sparse matrix computation because you have algorithms that are only taking memory proportional to the non-zero elements. Okay? So M is just a small number times 10 billion. Okay? Of course, you have to be a little bit careful. If there's dead ends, you have to make sure that the probability becomes 1. Remember, the beta doesn't work if you have a dead end because you never jump out of it. It has to be 1 here. So you have to be a little bit careful, but that's not very complicated. So it's slightly more complicated than just this because you have to be worried about the dead ends. If you look at what we did before, basically here, this here. For a dead end, you have to put a 1 here because these are all zeros. Okay, so that's basically the thing you have to worry about. And then you have a lot less memory. It's still big, It's still very big, of course. You have some multiple of 10 billion numbers here. The computation is still huge. And in fact, in order to do this, Google basically invented the concept of a data center. The very first Google engine was just a few machines. But since the web was growing exponentially, the number of machines was growing all the time. They always had to do this computation. So eventually, they had to come up with a way of managing such a large number of machines. So they invented this concept of a data center, okay? And so it came because they had to do this computation, okay? So and then you get something like this. So here you have a graph. Here each of the node sizes is proportional to the page rank. So B and C are very important pages, but all the little purple pages are not so important. Okay, so that's PageRank. But PageRank is not the end of the story. There's some problems, okay, with PageRank that we're going to solve. So first of all, PageRank is doing generic popularity in general. But what if I'm interested only in Star Wars, for example. I don't care about Star Trek, okay, which is garbage. I only want Star Wars, okay? So I don't want the popularity, even if Star Trek is much more popular than Star Wars. Actually, my real opinion is the opposite. Okay, so we have this topic-specific PageRank, where we want to find the importance with respect to topics. That's one thing. Okay. Another problem with PageRank is cheats. Okay. Artificial topologies, which are called link farms, which I will explain. So you need to somehow get around that. So, of course, the real solution Google is doing today is kind of secret, but we know some techniques for getting around that. Also, hubs and authorities can be important too. So PageRank is only a single number, but remember when we introduced it, we started by talking about hubs and authorities, and sometimes it's useful to have these two concepts. So an authority is really the source of the information, and a hub is pointing to information. Sometimes it's important. So these are kind of limitations of PageRank. And what I want to do now is explain a little bit how to solve this. So the first thing I want to talk about is kind of a generic one, the topic specific. How do you make PageRank work for specific topics? Okay. So we have this random walk, but we want to somehow push the random walk so it only looks at the pages that we're kind of interested in, the topics. Okay, so we give more influence to web pages that are close to some topic, sports or travel or whatever. That's kind of the general idea. But the way to make it work is you change the teleport. Instead of teleporting to a random page anywhere, you only teleport to relevant pages. Somehow you have a subset of all the pages, and there you can look at keywords and so on. All the pages that are about sports, and you only teleport to that. So that means the random walk is somehow staying inside this relevant area. Okay? You can even be smarter, you can even assign weights. You can have some pages that are doing sports are more important than others. So there's many ways, but basically the idea is you change the teleport set. Okay? And with that, then you do a regular PageRank calculation. So you really don't have to change the algorithm so much. Okay? So the teleportation set. Okay? So we recalculate the PageRank with that. Okay? And the idea is you can pre-calculate PageRanks for different topics. Okay? The only trick is somehow you need to get this teleport set. What is the set for sports and what is the set for something or whatever? So there's many ways. You could, for example, take the sets from regular classical information retrieval, which means you look at the words, previous generation, that's one way. Or you can look at the context, where the query is coming from, okay? You could look at browsing history, you can look at cookies. So there's all kinds of tricks to get the right teleport page, okay? That's one way to do it. So the real PageRank, of course, has a lot of different topics, and they're all kind of done together. Okay, so that's one thing. That's kind of topic specific. Let me talk to you now about another application, which is kind of like PageRank, which is called SimRank, similarity. And to show you that, let me give you an example. So here's a graph, right? And somehow I have node 1 here, and I have node 4. And my question is, how close are they? Are they like each other? So the point is now similarity. Yeah? I want to find similarity, and PageRank can help. So here's another node, 7. And the question is, how close is 7 to 1? And then you can say, which of these two, 4 or 7, which one is closer to 1? Which one is more similar to 1? Okay. And shortest path doesn't really help, because in both cases, the shortest path is 2. Fine, so it's actually the same distance. But maybe maybe some of them are similar. One way of looking at it is the number of paths. If you go from 1 to 4, there's many ways. So you can go 1, 2, 4, you can go 1, 6, 4, 1, 5, 4. But from to 7, there's only one path. So there's many paths from 1 to 4. So maybe that helps. Okay? And all these different ways to get between nodes maybe have some importance. Maybe 4 is maybe more important or closer to 1. Okay? So what do you think? Can we do something PageRanky to figure out which one of these is closer to 1? Actually, we can. And we can do like a random walk thing. We can start from node 1, and we can do random walks. And we can see how often we end up with 4, how often we end up with 7. And so we can figure out which one is closer. Okay? So here's another example. We have 4 pictures and 3 objects. A house, a tree, and a mountain. Okay. And the question is, how similar is picture 1 to picture 4? Or picture 1 and picture 3? So 1 has a house and a tree, 4 has a tree and a mountain, but 3 also has a house and a tree. Okay. So maybe 3 is like closer. Okay. So we can actually use a kind of PageRank algorithm to figure out how nodes are close to each other. Okay. So again, we're going to start with a random walk. So you can see this random walk idea is actually very powerful. Huh? You can do lots of variations. Okay. Oh wait, this is not the... yeah, okay. So this is the topic-specific PageRank. But what if, instead of having a set, I always start from one node? What if the teleport set is the initial node itself? What if I always start from picture 1, and I do random walk from there? And then I see what happens. Okay? This is something called SimRank, similarity rank, and this one, the teleport set, it's not topic specific, but it's always the starting node. And if you do then PageRank, it'll tell you how pages are similar to that node, because the topic is my original node. Huh? It's not sports pages, but it's my original node. So instead of finding nodes that are related to sports, I find nodes that are related to my initial node. Okay? So that's the SimRank idea. You walk from a fixed node on k-partite graphs. Okay? And so this is a specific algorithm. Huh? You have, for example, authors, conferences, and tags, topics. Okay, and you want to know which of the authors are kind of similar to each other, so you can do random walks or similar to another one. Okay. Okay, so this means you have to do it, of course, for every node. For every node U. And just as a final comment on this, there's a software, a system called Pinterest that you may know, which collects information and photographs and stuff. And Pinterest is using something like this, okay, to figure out things that are similar, okay? This is also called PageRank with restarts. You restart with you all the time. Okay, so let's go back to our example. So what is the most related picture to pick one? Okay, so you start PageRank, but the teleport is just pick one. That means whenever you teleport, you go to pick one. Boom, back to pick one. Okay, random walk with restart. So this is the matrix. Okay, but if you do the actual matrix with teleport, so this is the original matrix. You can see there's two parts to it. There's this house tree mounted part and the pictures. But you can see here, you have the teleport. Whenever you teleport back to picture one, which is row one. Whenever you teleport back here. And so you're basically doing PageRank, okay, with a teleport only to one of the nodes, okay? And then you can get some values. If you look at the values here, you can see pick one has some value, but the highest value of the pictures is pick three. So pick three is the closest to pick one, okay? And in the other example, where we had 1, 4, and 7, you can see 1 has, of course, very high, because 1 is very similar to itself. But 4 has 0.24, and 7 has 0.07. So 4 is more similar to 1 than 7, according to this algorithm. Okay? So this is a variation of PageRank that's also used, for example, in the Pinterest website application. Okay, let me summarize now PageRank, and then we'll talk about spam. Okay, finish up with the nice spam calls. So the normal PageRank, so it all differs because of teleportation. The normal PageRank will teleport uniformly at random to any node. Okay. All nodes have the same probability of the surfer there. Now, topic-specific PageRank is teleporting to a specific set of nodes, but then it's using the regular PageRank, okay? And the random walk with restarts, which is the SimRank, is the teleport is always to the same node. So it's like the topic-specific is just one node. We want to know the nodes that are similar to this one node. So this is different kinds of PageRank, okay? But now let me finish by talking about spamming. Spamming is a very neat topic. Web spam. So the web and the spam was invented at the same time, okay? The spammers were immediately active when the first websites came. So web spamming is a deliberate action to boost a web page position in the rank. So to boost the ranking, deliberate. So that has nothing to do with the real popularity, but you do something to boost the ranking. And there's probability, this is used a lot, and 10 to 15% of all web pages are actually spam pages, okay? Pages appearing in your rank results should not be there. And there is actually a clean way of calling this cheating. This is called search engine optimization. That's the official name. There are companies that make their living doing search engine optimization. Okay? Basically cheating. You pay them and your rank increases. Okay, so let me explain how it works, but let me start with the very early ones. And then we'll explain how it works with PageRank. Okay? In the very early search engines, early 90s, they indexed the pages by the words they contained, and they respond to search queries with the pages containing those words. So if you want to talk about football games, all the pages that talk about football are indexed. Okay? okay? And somehow you have some tricks, you try to find which pages are important. How do you figure that out? This was before PageRank, yeah? Well, the number of times, pages that talk a lot about sports were important, or maybe the sports word is in the header, the title. Okay, so it's very easy to cheat, to do that. So the first spammers were trying to exploit this. So for example, I am a shirt seller. I sell shirts on the web, shirts. And I want people to come to my website. So I'm going to pretend that my website is about movies. So when people type about movies, they come to me. Okay? So how do I spam it before PageRank? How do you make your page appear to be about movies? Well, the simple trick is you add the word movie 1,000 times, and you make sure it has the same color as the background color so nobody sees it. Okay? This is what this you do, so only the search engines see it. Or you run the query movie. This is smarter. And you see which page comes first. Well, you take the content of that page and you copy it into your page, making it invisible. Of course, that will supposedly make your page more important. Okay. This was all before PageRank. This is called term spam. Okay. This was before PageRank. And Google had a solution then, very early to term spam. And the idea is you don't look at the text on the page, but you look at the text of the pages that link to you, what people say about you. This is what's called the anchor text. So the anchor text is the text in the link. When you click on it, it goes somewhere. So that is a page pointing to you. So that solves most of the term spam problems. And of course, with PageRank, this also kind of solves the problem. So the shirt seller doesn't work, okay? Because even if he says he's about movies, who cares? He won't be ranked very high for movies, okay? So he will not get the links. Okay, good. So what do? Well, you can actually cheat in a smarter way. You create 1,000 pages and fake pages, and each one has the word movie in the anchor and links to it. But they have no inlinks. So it still doesn't work, okay? Too bad. Doesn't work. So what do? Well, I give you the solution now. You do spam farming. So let me now give you an explanation how to do it. So spam farming, it's also called link farming, is a way to increase your ranking in PageRank, and it works very well, or it did until people figured it out. Okay, so here's a famous example of it. This was in the good old days when George W. Bush was president of the United States, and you type miserable failure into Google, and it returns the biography of Bush. Okay? This is called Google bombing, and people love to do this. Okay, you can find there's many examples of this kind of coordinated attack to raise the rankings. Okay, let me explain now how spam farming works. Okay, so the idea is you want to concentrate the page rank of a single page. You want to improve the ranking. You want to create structures, link structures of web pages that increase the rank of a particular page. So how does that work? Okay, so here's how it works. So I'm a spammer. So from my point of view, there's three kinds of pages. There's inaccessible pages. This is pages made by other people. I have no way of accessing it. There are accessible pages. This is pages made by other people, but I can actually modify them. They could be comments, or reviews, blogs, whatever, I can add stuff. Those are accessible pages. So they're pages owned by other people, but I have access to them. And the third one is my pages, the ones I own. So I have a bunch of machines sitting in a room, and they have many pages. So these are my own pages. So there's three kinds of pages. And if I do it right now, with these three kinds of pages, I can increase huge the rank. So here's how it works. So here's the web. Here is the page that I want to increase the rank, okay? And I want to maximize the rank of page T. Here is the accessible pages. So these are the pages on the web that are owned by other people, but I can still add things to them. They're like blogs, I can add comments, whatever. And there's lots of ways of doing that. So these are pages that I can access and add stuff to. And I can add links in there. And the others, the blue ones, most of them are blue, are inaccessible. They're pages made by other people, and I have no way of changing them. And there are a huge number of those, of course. Okay? So first of all, the first trick is you link to T from as many accessible pages as possible, of course. That's not enough, huh? That's the first step. You link to T from as many accessible pages as possible. And now you construct what's called a link farm. And this will give you kind of multiplier effect. And let me show you how it works. So these red pages are owned by me, the spammer. These are my farm pages, okay? So the farm pages, so page T links to the farm pages, and the farm pages link back to T. Okay, so these are mine. Okay. Now, what happens? So all the red ones are owned by me, okay? So now let's compute what the page rank is here, okay? Of course, there can be millions of these, and they can be shared between different page T. The search engine optimizer will have many, many of these, okay? Okay, so now how does it work? So this actually works. So how does it work? So let me explain how it works. Assume now you have n web pages, the blue n, and you have m farm pages. Okay? And now let me make some definitions. So little x is the page rank value contributed by the green pages. So which could be some small number, but there's some number. So that and little y is the page rank of T. Okay? So now let's do some computations. What is the rank of these farm pages? Okay, the rank of a farm page, okay, you can compute it. It's, this page has a certain rank, y, and there's m farm pages, okay? So when you do the random walk, you have a beta probability of leaving here, okay? And you have divided over m. So you have a contribution of beta y over m from page T. You also have a contribution of 1 minus beta over n from the regular PageRank teleportation, okay? So each farm page has this rank, okay? Right? You see that? That's how we figured it out before. We can now write down and say what is y equal to. The PageRank of y is the PageRank of x, which is the contributed by the green one, plus some number, okay? Plus each of these farm pages will contribute something, So there's m farm pages, big M, and the random walk multiplied by beta. So it's beta times m times the rank of the farm page, okay? Plus, of course, the 1 over beta over n is teleports, See that? You understand that formula? It's just our the formula that I apply on y. I can simplify now. Now you notice you have two things here. I have two factors of m here. I have the m is in the denominator. It's divided by how many of them, but I have it multiplied by, I also have m of them, so it's also multiplied by m. Okay, so y is equal to x plus beta squared y plus 1 minus beta times m over n plus this very small number, okay, which the last one I can ignore. Okay, so let's simplify this. Okay, so we ignore the blue one. So y is equal to, so here we have y on both sides. So we have y is equal to x over 1 minus beta squared plus some constant times m over n. Okay, m over n. Some constant times m over n. Okay. So the constant is beta over 1 plus beta. So it's not so small. So it's like similar to 1/2, a little bit less. So some constant times m over n. So now you can see how to increase the PageRank of y. It's very easy. Okay? It's very easy. The bigger that n gets, the bigger that y gets. Okay? If I have a million pages here, then I will add some value. Of course, I need a large number of these, but they don't have to be very big. They can be very small pages. It's just I need to have a lot of them. Okay? So increasing the size of m will increase y. And of course, another way to increase y is you start by having a lot of accessible pages. So you have two effects. You increase x, but you also increase m. So you can see the contribution is somehow proportional related to m. Okay? Okay? And it works because I divide my m pages, but then I multiply by m because each of them contributes to t. Okay? See how it works? Link farming? Okay? Another thing is, you don't have to actually make m very, very, very big. It just has to be bigger than your competitors. So let's say you have a competitor. I'm selling shirts, and my competitor is selling shirts, and we're kind of similar companies. I just need to be a little bit higher than them. Okay? So m doesn't even have to be that big. I just have to be a little bit bigger. Of course, the competitor is looking at me and also wants to be a little bit bigger, and the search engine optimization guy is very happy because both of them are going to be paying him to go higher. Okay? So you see, so that's how link farms work. Okay? Okay, so how do we combat this now? Now I want to show you a little bit how Google fights this. This still exists, and of course the techniques used today are even more complicated. Now, this was a few years ago, this was state of the art, but not anymore. How do you combat this? Well, of course Google does not like this because it reduces the value of the search engine if they give you spam. Okay? What can they do? They can blacklist spam farms. Okay? Or you can do an algorithm called trust rank. You teleport only to trusted pages. So some pages are usually very good. Like university home pages tend to be quite good. EDU domain tends to be good. Or you can add good pages. Okay? And it's very rare for a good page to point to a bad page. So one way of fighting spam is that you don't just teleport everywhere, but only to trusted pages. Okay? So again, it's like topic specific. Instead of going to a topic, we now go to trusted pages. Okay? So each page gets a trust value. Okay? And trust is like a fluid also flowing around, and you're computing trust. It's like PageRank, but only for trusted pages. You can see that this teleport set is very important. Huh? Okay, so now we at Google, and I want to pick a good trusted set. I need a trusted seed set. So some of them have to be picked manually, and some of them can be done automatically. Okay, but I need it to be big, but also it's small because humans are doing it. So how do I do it? Well, I can use PageRank, kind of recursively. The top K pages, the really top pages, are probably good or trustworthy. Or I can use trusted domains, edu, mil, gov domain, maybe. Or I can, it's actually not a good idea to mark as spam all pages below a trust threshold because new pages tend to be ignored. So that's not good. So how do we work it? Well, basically the idea that works is called spam mass. So the way you do it is you calculate two values of PageRank. So here's a page. Here's a trusted set. And the question is, what fraction of the PageRank comes from spam pages? So some spam pages here, a trusted set. How much of the PageRank is due to spam and how much is real honest PageRank? So we don't really know. Okay, so we calculate two PageRank values. We calculate the regular RP PageRank, but that has the spam in there. We don't know how much spam, okay? And then we calculate another one, RP plus, another PageRank value, but only coming from trusted pages. And that might be different. That value might be different. And the difference between the two is considered to be how much PageRank is coming from spam. So if the trusted set was kind of representative of all of the pages, and there's no spam, then these two would probably be almost the same, okay? And the spam fraction would be 0. But because of spam, it's not going to be 0. So we're going to calculate the difference in the PageRanks divided by the absolute. So this is a relative value. So this is called the spam mass. It's the percentage of PageRank that is coming from spam. Okay? And you can calculate it if you know a trusted set. And the nice thing is that it's relative and not absolute. It's a percentage. Okay? So it doesn't depend on the absolute value of PageRank. So you calculate not just the PageRank of a page, but the spam mass of the pages. And pages with high spam mass are considered to be spam. Okay? So that's one way of getting around this linked farm thing. Okay. So that basically tells you how to cheat and how to defend yourself against cheaters. Okay, so let me finish for today. So today we made kind of deeper study of PageRank, random walks. So PageRank is just one of many powerful techniques, okay? It's a form of random walks. So we started by studying random walks. We represented them by matrices, and we showed that eigenvalues and eigenvectors are important, okay? Then I explained PageRank, how the history of web. The problems with PageRank, first of all, what happens because of the big matrices, how you target PageRank, so the teleporting to specific topics, how you use PageRank for similarity, and finally, how you do link farms to cheat, and again, how you use teleport from trusted pages to estimate the spam mass so you can find the cheaters. Okay. So I think that gives you a good overview of the whole world around PageRank. You can see it has a huge number of things, and I only gave you some subset of it. And it's not finished yet. Today, Google is still doing things. Search engine optimizers, they still exist today, okay? So the battle is still going on, okay? But at least now you understand kind of what it's doing. Okay, so let me stop there. We're still a bit earlier, but that's not a problem. So that's all. Thank you very much.